Why does ice turn into water and water not into ice? The answer is pretty simple. Temperature, obviously. Actually, there's an underlying concept that dictates which chemical reactions go and which chemical reactions don't. This concept is known as entropy. The most commonly used definition of entropy is the degree of randomness or disorder. People think more randomness or more disorder means more entropy. However, this is extremely misleading. If you look at this Rubik's Cube, would you say it's random or disordered? Chances are you probably would. And even though a jumbled up Rubik's Cube is pretty random and disordered, entropy is actually a measure of energy spread of a substance. For example, if you look at the air around us, we see that it has certain particles. Each of these particles possesses some kinetic energy. However, since the particles are so far spread out, we realize that the energy spread in air is extremely high. Therefore, air and other gases have a higher entropy. I hope you now understand why entropy is not actually randomness or disorder, as well as why this definition can be misleading. Therefore, this Rubik's Cube, although very random and disordered, has a very low entropy.
The second law of thermodynamics states that in a spontaneous reaction, the entropy of the universe can never decrease. A spontaneous reaction is one that occurs without continuous human intervention.
Just because the entropy of the universe is always increasing according to the second law of thermodynamics doesn't mean that gases can't turn into solids. In fact, if we were supposed to take all the particles in this air that possess some kinetic energy and compress them together, it would form a solid.
If in a box we had red ping pong balls and blue ping pong balls, and they were arranged on either side of the box and then were shaken vigorously, we would see that the ping pong balls won't be in the same position in which they were in the beginning, as that was highly ordered and they were each on either side of the box. We now can understand that the ping pong balls can have a number of possible configurations they can take inside the box when the box is shaken. And even though the probability of this is very, very low, the ping pong balls can even go back to the original state in which they were. I hope this makes clear why the particles in the air can actually occur closely packed together and match the configuration of a solid, and also why the probability of this happening is extremely low.
Now let's try and look at a situation where a substance actually does go from higher entropy to lower entropy. We know that energy always moves from an area of high temperature to an area of low temperature. We also know that changing water to ice requires a great deal of energy, as it requires a change in state. As water turns into ice and its temperature decreases, the total entropy increases, and as the energy required to do that is extremely high, the entropy is also therefore very high. Therefore, the universal entropy increases.
As the second law of thermodynamics talks about the entropy or energy spread continuously increasing, there will be a point where the largest source of renewable energy will eventually exhaust itself. This largest source is the sun, and the phenomena of its energy being so far spread out that it can no longer allow any reactions to occur is known as the heat death of the universe, and is the best guess scientists have at how the world will end.